So, welcome everybody, and thank you for joining us today. My name is Laura Denale. I'm from Euronovia, and we are the partner in charge of the communication and dissemination activities for the SCORE Horizon 2020 project. This is the fifth webinar we are organizing within the SCORE webinar series, and it is dedicated to predicting the effects of climate change on coastal cities, going from the global to the local scale. So we will present the approach and models for downscaling. The webinar is led by our project partners at LAMMA, which is a public research consortium owned by the Tuscany regional government and the National Research Council in Italy. So here is the agenda for today. Just a few practical information before we start. Due to the tight schedule, we are not taking questions for after each presentation, but we invite you to write down your questions in the Q&A tab or in the chat that you have here on Teams. And you can do it at any time during the webinar, but we will answer them during the Q&A session at the end. And I also inform you that the webinar is being recorded and it will be made available in the next days in the SCORE YouTube channel. If you're interested to know more about our projects and activities, we invite you to visit our website and follow us on social media where we are very active. So thank you again for joining, and I now give the floor to our first speaker, Carlo Brandini.
Hello, good morning to everyone. I'm Carlo Brandini from the Institute of Marine Science of the National Research Council, Italian, and also from LAMMA Consortium, which is a joint entity, a joint consortium between the CNR and the Tuscany region government. We did the project, we are leading one of the work packages, namely the work package 3 that is dedicated to predictions, long-term predictions or climate prediction of the effects of climate change on the coastal cities involved in the project. With me, there are several colleagues that will in turn will speak this morning. Close to me, there is Massimo Perna, and from remote connection, we will have our colleagues Stefano Taddei, Andrea Cucco, and I think Julia Anton from ATU, and also hopefully Michele Bendoni will join us later. Then I'm sharing my screen, and I will start the presentation. If you, I'm just asking for if you are able to see the first slide. That is essentially the title. So from global to local scale, predicting the effects of climate change on coastal cities. As we have essentially two scale of interest. One is the scale of the Earth system, what we call global, the scale of the coupled dynamics between atmosphere and all the possible spheres, so the domain of water, the hydrosphere, which is essentially all the water component of the Earth system, so the oceans, the rivers, the lakes, and so on, the cryosphere, so the ice domain, the lithosphere, so the land domain, the biosphere, all of these spheres are strongly connected with each other. But when we say global, we refer to typical scale of the order of 1,000 kilometers or even more, 10,000 kilometers, up to a small dimension that typically depends on the we will see, but what in the model we call resolution, while the local scale is the scale of our everyday life, no? So the scale with which we measure the effects in our everyday life, the scale at which we also, thinking to the project, we evaluate the effect of climate change resilience strategies. As for the project, the ecosystem-based solution, the financial resilience, and so on. So the typical scale of when we say urban or local is 10 to 1 kilometer, and as a small dimension, we refer to something that can be 10 meters or even less. So what this small dimension is, as I said, in models, for instance, in global circulation models, is something that is necessary to represent large-scale dynamic features. So the large-scale domain of the Earth system, describing the dynamics of air masses on water masses, so the major winds and currents, the areas covered by ice, and so on. So when we refer to resolution, we refer to the resolution of so-called eddy resolving models as eddies, so major cyclonic or anticyclonic disturbances on the atmosphere or in the ocean need this kind of small-scale feature resolution to be correctly represented. And as I said, this can be of the order of a few tens kilometers. While in the local scale, we are interested in understanding the effects of very small features that can be at the scale of single buildings. So describing the flood on a urban district or even on individual buildings. This is the domain of the urban hydraulics. So at the global scale, we have a number of instruments like satellites, like large measuring observing networks, with which we measure the effects of global climate change. So we know from the reports of IPCC, for instance, that temperatures are increasing, our planet's becoming hot and hot as greenhouse gas concentration rise. We observe more frequent and intense extreme phenomena that can be floods, that can be also increased drought condition, but also more severe storms, heat waves, both in the atmosphere and in the ocean. So in this last case, we refer to Merv heat waves. There's the major effect on our coastal areas that it is due to melting ice. So we have in overall a warming, rising ocean, and these affect, of course, even the coastal floods together with the observed change in the global circulation of atmosphere and oceans. But still, we are such global scale. What is important to say is that global change effects are not uniform on Earth. For instance, for what concerns sea level rise, one can imagine that this effect is more or less uniform on Earth. And this is not the case, as for instance, for the observed distribution of sea level rise trends, we have that the regional trends can be very different from any different area on our planet. So there are remarkable spatial differences due to thermal expansion, isostatism, changes in global circulation. So all of these different dynamics affects in a different way the spatial patterns of sea level rise, or that can be also affected by internal dynamics of the Earth system. So in this case, the decadal scale oscillation. Downscaling is a key word. Downscaling means we take known information at large scales, and this typically comes from climate models that are provided by climate services, for instance, the Copernicus Climate Change Services or C3S, to make prediction, and we downscale this information up to local scale to make predictions. This is an attempt to bridge the gap between global and local effects by nesting. Nesting is something that really looks like a telescopic effect. No? So this is the reason why we add this small icon, because we can think to downscaling, nesting different models with increasing resolution. This is not always the case. For instance, we will see we adopt unstructured grid modeling strategies in which this kind of telescopic effect is directly inside the model itself. But still, this kind of scaling global model solution up to what we call the last mile, the urban scale, that is not so trivial, as each scale has also its own characteristics, because at each particular scale we observe different physical processes, and this is the reason why at a certain point we will have a kind of step. So the first step is that of what we call exactly downscaling climate models, and we'll see how. While the second step is the urban scale, because at the urban scale, at the last mile, we need to describe differently this kind of physical processes inducing, for instance, land flooding. So the effects are not independent from each other, and this is the reason why we need to define a common forcing for all our models. So the effects combine with each other, they do not act independently from each other. So, for example, Andrea Cucco in one of the next presentations will show you what happens in Venice, for instance. A major atmospheric cyclonic disturbance, an hurricane, not only is the cause of a strong wind condition, but in turn is associated, these conditions are associated with an area of low pressure that also induce an increasing sea level, and it can also, normally comes with heavy rainfall. So there's a combined effect of land and sea coastal flooding. So there is a need that this climate projection data, when applied on a urban scale, take all these coupled effects into account. So they must be produced by the same coupled simulation. So how all these components, we can say, match together to at a urban scale, and how we can compute these climate effects at a urban scale. So by using all possible information coming from different models. So wave models, as waves are very important, especially in the coastal area. They by themselves cause coastal disruption and coastal erosion. They contribute, they also give a major contribution to coastal inundation by increasing the sea level along the coastline. Then also hydrodynamic models, which are not the same model as the same models we use for wave prediction, are needed for predicting sea level along the coast. Which kind of combination of short-term effects, so storm surge, tidal condition, and so on, and long-term effects, so the signal of sea level rise, combine to modify the levels along the coastline. And also hydrological models are very important for coastal cities in each urban scale, but of course even here, as river floods are directly determined by hydrological processes in which rainfall is the main, not the only atmospheric forcing, but of course the main one. So different models, and this is essentially the slide that is a summary of our work in SCORE. So what is the SCORE approach to downscaling? So we start from data from global circulation model, so provided by the climate change services inside Copernicus, that normally has several possible models to choose, and we choose some specific models able to provide all the parameters of interest that are not only one. So we need wind, we need solar radiation, we need rainfall, and we need all these parameters at a good resolution that is normally provided by atmospheric circulation at a regional scale. This is the second step. So by regional circulation models that are also provided by Copernicus. These models are used to force three kinds of models, as I said, that we use for downscaling. So an hydrological model that describes all the processes from rainfall to water discharging rivers, sea level models able to describe the effects of wind, atmospheric pressure, and tide on water level along the coast, and a wave model that describe all the processes by which winds generate, blowing on the sea, all the processes causing wind formation, wind dissipation, and the transfer of energy from offshore areas up to coastal areas. This is what we will call in the next presentation slot the step one of this downscaling procedure. So in this case, we are from global to, we would say, regional scale, and then we will have the urban scale model. So the hydraulic models and the initial wave model. So the model we use to simulate what we call the last mile. Finally, all these kind of downscaling model are run together in different conditions. One is called hindcast, so we use essentially the so-called models, projection model using in the so-called evaluation mode. Then we have the historical run, in which essentially we run the models for the past as in the validation phase, but essentially to compare models from a statistical point of view, as what is essential in climate modeling is to reproduce the same statistics, not exactly the same sequence of time series. This is provided by the evaluation part, in which models are also assimilated. So there is kind of merging between observation and simulation. Then there are two major projections, as we know that the predicted long-term conditions can be more severe with respect from the more affordable scenario. So we compute the effect of RCP 4.5 scenario and RCP 8.5 scenario provided by climate services. And from all these time series, we need to compute urban scale scenarios, we need statistics. That's why at a certain point, Julia will tell us which kind of statistics we need to produce, for instance, the flooded area with the flooded, the river discharge, or the marine parameters with a return period, with a given return period that can be 100 years or 500 years or more. So this is accomplished through extreme values analysis. So from this introductory part is all, and now I'm giving the floor to Stefano, who will introduce the step one part of this downscaling procedure. So that's at the moment all from my side. I'm giving the floor to Stefano.
So my name is Stefano Taddei, and I'm a researcher in the Lama Oceanography Group. And I'm working on numerical ocean modeling and also on ocean monitoring with instruments like, for instance, HF radars for surface currents, buoys, DCP, and other instruments. This presentation is about ocean wave simulation in the framework of the SCORE project. But let's first see why we are interested in wave simulation. As Carlo already explained, ocean waves can cause destruction, coastal erosion, and contribute to coastal flooding. And in particular, in the case of storm surge events, like here, where I show you some example of extreme events that occurred in Italy. The last one in December, last December in Tuscany, was in Livorno, which is the city where I live and where I work. In fact, also the Lama facility in Livorno had some damages from the storm surge. I can show here two very short movies in order to better understand how it works. Can you see the movie now?
Yes.
Okay. As I was saying, you can see the water coming from the sea and the street completely underwater in Livorno, the last December. And here in Liguria, you can see very well the run-up of the waves, which is quite high here. Just to have an idea of what happens. Okay. So can you see my presentation again?
Yeah.
Okay. So how can we model storm surge? There are a number of different factors that contribute to the storm surge. For this reason, different kind of models are needed. In particular, you need to model the water level and the wave run-up. But you need a specific model to do this, and they will be described in the next presentations. Here, we focus on what happens offshore. We want to model the waves offshore, but this modeling, it's important also because you need to give some parameter to the models that you need to model the phenomena close to the shore. So first, let's see, before speaking about the models, let's see how the waves are generated. The ocean waves that are of our interest are the so-called wind waves. They are the results of the interaction between water and atmosphere. And when the wind starts to blow, waves of a few millimeters are formed, and they are called capillary waves or ripples, and they stop if the wind stops. But if the wind continues to blow, these capillary waves grow and become gravity waves, which do not die out immediately when the wind stops, but can propagate and become, for instance, so-called swell. The height of the wind wave in deep water depends obviously on wind intensity, persistence, and also the fetch, where the fetch is the length of the sea area over which the wind has blown without obstructions. Clearly, the longer is the fetch, the more energetic the waves will be. The ocean waves are also affected by dissipation, which is the main mechanism of dissipation of energy of the waves that acquire energy from the winds. And then there are also wave-wave interactions. So we need to model all these phenomena to build physical models that we can solve. And there has been interest in the wave modeling from a very long time ago. In particular, it increased during the World War II because it was very important to have good marine forecasts. So we are now at the third generation from the 90s, at the third generation models. And they are called phase average models and solve the spectral action balance equation, which is a differential equation of fluid dynamical equation, and as forcing terms that take into account wind interaction, dissipation, and nonlinear wave-wave interactions. Here you can see just as a curiosity the differential equation that must be solved. Some of the models of this kind are WOM, WaveWatch 3, S1, for example. These differential equations can be solved numerically by discretizing them on a grid of points. And different scales from global to regional can be resolved by nesting regular grids. Regular means that the mesh is the same and the resolution the same everywhere in the domain. We can make a nesting of these grids with narrow domains in a higher resolution. As you can see on the column on the right, you take the boundary condition from the larger domain, larger but with lower resolution, and you can use those boundary conditions in the model on the smaller and higher resolution domain. The model that we use in SCORE is the WaveWatch 3 model, which also allows to use not only regular grids, but also the so-called unstructured grid. This means that the resolution of the grid, it is not the same everywhere, but you can increase resolution close to the areas where you need more accuracy. And there is a small picture here, but I can show you also another short movie in order to understand what means increase the resolution in the different areas. Can you see the movie?
Yes, we can see it.
Okay. So you can see the zoom in the European area. This is an Atlantic model. This is the Mediterranean. And we'll have a further zoom on the Massa, which is one of the cities of our interest, where we reach the resolution of about 500 meters close to the coast. So in this way, you don't need to make the nesting process that we have seen before, but you can use in this case just one grid. So we were arrived here. You can build these grids by using free code like Gmesh and coastline free data like GS, HHS or OpenStreetMap, and bathymetry databases like Emodnit and GIVCO. You need also the forcing field because the model need the information on the wind in order to force the formation of the waves. And we take these winds from the Copernicus database, in particular the MEDCordex or EuroCordex projects, And what we need for the wave model is the near surface wind components. We also need, not in the Mediterranean, but for instance in the Atlantic model, even the sea ice refraction in order to take into account the effect of the ice. Here there are some the main steps, 4 steps of how you set a simulation run, but just to show you that there are different steps. First, you need a pre-processing step where you prepare the grid, the forcing files that WaveWatch 3 can use by using some specific routine. Then you run the model with the WW shell routine. And the third phase is the post-processing phase, where you extract from the raw files the point of grid data and put them in netcdf files for further analysis. Just to show you some examples, here we have a study case in SCORE, which use the Eurocordex wind data. And you can see here different zoom of the waves, the significant wave 8 maps. You can see the whole map, then focus on Europe, and finally at the bottom on the left a map of Sligo, which is another city of interest in SCORE. You can see that the resolution is quite high, and it's I was saying before about 500 meters. And then you see also a comparison of the time series of wave 8 data. These are the simulation made by the reanalysis data, the evaluation data, compared by some voice data. You can see that there is a good agreement. And here another case of Massa, where you can see the maps and also a comparison with the Gorgona buoy, which is...
So I'm Andrea Cucco. I'm a research scientist in physical oceanography at CNR in Oristano, Italy. And I'm going to introduce some of the methodological aspects and some of the results obtained within SCORE to make a future projection of storm surges in the different coastal city labs and the related increasing of the seawater level. Just a few words about what the storm surges are. The storm surge can be defined as a mass of water masses, seawater masses that are pushed toward the coast onshore by the action of meteorological forces, mainly wind and the low atmospheric pressure. This can be generally a cause of great damages in terms of structures and also injuries, and sometimes also death. And if specifically in phase with, for example, high tides, high level of astronomical tides, you can have the generation of extreme events of storm surge that led to flooding and inundation. The well-known case is the city of Venice that is often hit by this kind of events. This is events occurred several years ago, about 20 years ago in 2002, when the seawater level reached the 144 centimeters above the sea level, and at that time it was considered an extreme event. This is young me taking a rest after a walk on the water. And what happened now? Nowadays, how is the situation? The situation is worse and worse. We have an increase on the intensity of the extreme events, both for the amplitudes of the storm surges and, of course, in the frequency. It's so evident that, for example, they had very strong Acqua Alta event, for example, in November 2018, with the water with sea surface high reached up to 187 centimeters above the mid-sea level. But the year before, in the Adriatic Sea, there have been another extreme event, another record, reaching with the sea surface area reaching the 156 centimeters. In that case, specifically, the contribution of the storm surge only was most of the amplitude of the water of the total water event. So about 140 centimeters. In that case, luckily the tide was at its minimum. But if there were been a different phase between the storm surge wave and the tidal wave, you could reach also up to 2 meter and centimeter high, generate a great disaster. So the numbers and the frequency of these such strong extreme events are so different from the past that we are in the time that we have to change the evaluation of the return periods of these extreme events. So what about the storm surge frequency intensity in the future? What about these events in the next 100 years? How do we predict storm surge events in the future? So there are several methods can be applied to make such kind of prediction. Some are relating with short-time prediction, so at let's say at meteorological time scale, let's say spanning from hours to weeks, and other more suited to make long-term prediction running for month to century and related basically to the climatological timescale. So we can detect 3 different type of methods, which are the first one is the so-called data-driven model, which are basically the statistical model. In the past, they were named in this way. Now are more known as machine learning methods, neural methods, and other type of such kind of methods. And these kind of methods are mostly useful in the short-term prediction. Then we have the deterministic model-based method, which uses basically numerical models, solving a set of partial differential equations, simulating basically the movement of the fluids due to different type of forcing. And with this deterministic approach, you can both make prediction in the short time scale and in the long time, let's say in the climatological time scale. Then in the recent years, there have been the rise of combined probabilistic and deterministic method that use both the approaches to improve the accuracy of our prediction. Within SCORE project, we move with a deterministic approach, and in particular use Scheife, which is a finite element hydrodynamic model suited for such kind of application. It's a three-dimensional model, three-dimensional hydrodynamic model based on finite element methods, which is connected. They include different numerical modules like a coupler for the wind wave simulation, turbulent closure model, both Eulerian Lagrangian transport model, sediment transport model, and water quality model. A few words about the way to use it that can be very helpful for people that would like to apply such kind of method. It's very easy. It's a kind of plug and play code. It's a open source code, freely downloadable at this link. You can see throughout SVN or GitHub. There are some prerequisites, which are the use of the needs of Linux operational systems and the Fortran and C++ compiler. And through few easy steps, you can access to the link, download through the SVN or Git browser, or directly download the zip file. So you have to unzip the file, and you proceed with the compilation. Also, in this case, very easy. I can show you a short movie. There are a few steps. Once you are in your directory, you access throughout the README to all the steps you have to do. The first one is to make first step, first time. Then you have to make a check software, make configure. And I'll show you. Make configure allow you to access to a graphical interface that allow you to check to select everything you want. Then you make the install, and finally you compile the code with make fem. If everything is okay, you will have your executable ready for running, which is Shifem, and you can move to the next step. Next step is the mesh building. Being a numerical model, you need a computational domain where integrate your system of equation in the space. And Shifeng uses the finite element methods to make its spatial integration. And to do this, you need to generate basically an unstructured mesh based on the finite elements. So composed of singular triangular elements of different shape and form. To do this, as already suggested by Stefano, you can access throughout the GMSH software that can be downloaded at that link. And in few easy steps, you can measure grid, your finite element grid. A prerequisite is just to have a cost line in geo format. Okay, so through few steps, you can select the size of your element dimension of triangles dimension. You can choose the attractor along the coastline that allow you to increase or to reduce the resolution of the elements with a kind of gradient. You can set the parameters of such gradient, and then you run your meshing, obtaining your finite elements mesh with a different resolution. This is the case for where we increase the resolution in the Belidor area, if I see correctly. Okay. And then after this step, you have to transform your mesh file basically into the Shifeng format, which is very easy. There is a list of nodes with the coordinates and a list of elements with the number of the nodes composing the vertices of each elements. So after that, the game is done. You are ready to make a fast run, launch your simulation. The last thing you have to do is to text a small file, which is a structured file, in which all the parameters that you want to apply to your model setup has to be defined. So the main ones are the output file names, the mesh file name, the reference date and time, the starting, ending, and time step, so the output features. Then you can set or not the bottom friction type and coefficient value, the wind drag type and coefficient value. And finally, if you have it, you can include the file with all the atmospheric forcing information. If you don't have it, you can set, let's say, synthetic wind, synthetic water elevation, the boundary, whatever. So coming back to our score project, how we behave, how we apply Shifeng to reproduce the future projection of storm surge intensity and frequency for our study cases. First of all, we group the study cases into different types, the one belonging to the Mediterranean area, the other in the Atlantic. Why? Because the two different basin environments are characterized by different environmental feature, different forcing, whatever. First of all, we have to define which is the wind fetch land impacting on the storm surge propagation for the different cases. We have to take into account the amplitudes of the tides, take into account the behaving of the atmospheric pressure, both for the absolute value and also for the atmospheric pressure gradients. And finally, the most important thing is to test the role of nonlinear interaction between the astronomical tides and the storm surge wave propagation toward the coast. To do this, to approach to this step, which is fundamental to select our final approach, I show you a test case applied for Sligo Bay in order to define which is the role of simulating, simulating at the same time both the tide and the storm surge, or in the favorable case, to avoid the simulation of the tide, to simulate just the storm surge and to add the displacements of the water level induced by that astronomical tide in post-processing. So let's say this is the second one is the linear approach, is the most easy. In the first case, we approach to simulate the storm surge and the total water level with a basin scale model approach. So meshing the area, the most of the North Atlantic area, where we suppose that the wind fetch and the atmospheric pressure dynamic is well included. And we made simulation just forcing our domain with the atmospheric forcing. So we don't simulate the tide. We just simulate the contribution of the meteorological forcing. And then in post-processing, we add the tides obtained from tidal gauges in Sligo, for example, to reproduce the total water level. In the second case, we have a limited area model approach in which we have the reproduction of the bay, and we have an open boundary where we impose our signal coming from the offshore, provided by already existing open ocean model, and including also the tide. So in the second case, we have the reproduction of both tide and storm surge and the relation between them. We compared the accuracy in reproducing the observation in both cases, and we estimated the differences. The differences are very low. It's about 3 centimeters in accuracy by using the first case or the second case. So we were more or less, let's say, happy with the basin scale model approach because it's worked fine. And this result is totally in line with previous application investigating such kind of testing. So we move basically for all our case study cases with the BSM approach, because we're testing the worst situation, which is the Atlantic one with very high tides. We did the same for the other study case, which is the Orso Aldea, Spain, and also for another one in Portugal. And then we taking in mind this approach, we move to the Mediterranean Sea, where the tides are very low, so we don't have any, let's say, tidal problem. We can sum it after the computation of the storm surge, so in post-processing mode, to obtain the total water elevation. So for what concerns the Massa study case, here we have some example of the procedures we follow. We tested different type of meshes in order to detect the most suitable for increasing the accuracy of our simulation. And we also made for all this kind of different computational domain setup, a set of calibration procedures, changing all the parameters involved into the simulation of storm surge wave propagation at coast. And finally, detecting the best set of parameters with, of course, evaluating the accuracy of our model setup. Once the model is calibrated, has been included into a modeling chain to reproduce basically the future projection of storm surge contribution to the total water level, for the example, for the Massa study site. So we ran the model for the 55 here regarding the historical evaluation scenario using the historical data set provided by Eurocordex, and then we moved to the different climate change projection scenarios, so the RCP 45 and the RCP 85, using also in this case the meteorological forcing provided by Eurocordex. The different time series obtained by all the simulation run have been provided along with the results from Stefano activities about the wave model, the information about the displacement of the water level of the astronomical tide in the Massa study case, and of course we have also the projection of the mean sea level variation at the monthly scale for this study case provided by the projection dataset, we provided to the, let's say, last mile modeling chain, who has the, let's say, the duty to reproduce basically the propagation of both waves and storm surge toward the coast, simulating the flooding and inundation at urban scale for the study site where this is necessary, of course. Thanks a lot. I leave the floor to my colleagues, Massimo, I think.
Hello, everyone. I'm Massimo Perna. I'm geologist at Lama Consortium, and my expertise is as a researcher, geomorphology and coastal monitoring through remote sensing and GIS techniques. And I now want to share in a second my screen. Okay, so in this case, we're talking about the hydrological model. Hydrological model simulates a flux or flow, or anyway, a change of water storage with time within one or more components of the natural hydrologic cycle. Basically, an hydrological model deals with different scenarios that may occur in a specific hydrologic basin, starting from water scarcity, for example, after a long-term or short-term drought, to estimate a drought recovery period, or water excess, as is in our case, and you can see it for an example of water excess, let's say, an event occurred in early November 2023 in Tuscany. Water excess to determine the effects of specific heavy rainfall on water discharge. So basically, the hydrological model, as we used in SCORE, we use to simulate a specific part of hydrological cycle, let's say, that is the part that's starting from an event, a precipitation event, which produces a runoff and a change in runoff and discharge rate. So the model, for each one of the cells you see here in this representation, simply start and for each time step we choose, that could be hours or weeks, or but in our case hours, try to model a number of to estimate a number of parameters, but we focused specifically on modeling the discharge rate to specific outlets of the river basin that is near the river mouth or in the coastal city, of course. So what we have is an event of precipitation and a change, as you can see in this graph here, a change a long time of the discharge. And so this is simply the output, one of the output we may obtain from our hydrological model. We choose a specific model that is list flood code, that is a model developed at Joint Research Center of European Commission. That's why we choose it, because it's a tool developed among the European Commission environment, and it's also open source and free. So that's another reason, of course, we choose it. And this is specifically produced to be used in transnational catchments, so large basins, but still a lot of people are still using it also in small basins, as we did in SCORE, where we had a very different size of basin. Also, this model can be used to assess flood forecasting and also assessing the effects of river regulation measures or climate change, that are all things that we are testing in SCORE. Okay, so very fast. We got a lot of inputs data set, that are meteorological forcing. We saw the same forcing we saw for the other models. I mean, the same type of data set used, but different variables, of course, since we talking about precipitation here. Anyway, always Eurocordex data sets, so data coming from Copernicus or anyway European data sets. And a large and a huge amount of static maps that provide information of morphological, physical, soil, land use properties of each pixel of the computational domain that you see in the picture. So we have meteorological forcing, that is for an example of total precipitation during a day of millimeters per hour, and an average daily temperature, and of course evaporation that can be downloaded and passed to list flood model, or can be derived using the tool inside listflood, that is ListVap, that is a component of a listflood model. And a number, as I said, of static maps, that is a digital elevation model, a flow accumulation, a local drain direction, and really a huge number of static maps to produce, and that's why we decided to write down a kind of methodology where that is still a work in progress, that may help to prepare and to pre-process data sets, static data sets, as you saw before, in a way according to list flood models. So basically, you can use this code to pre-process in our these data sets, and then give it to list flood model, and then run the model starting from a specific basin. So that's our effort in this direction. And specifically, we are developing still list flood in 3 coastal cities specifically, but in these areas we test and calibrate with Cordex evaluation scenario the run. Then we did the 2 runs with the RCP 4.5 and RCP 8.5 scenario, running in all the 3 towns. Specifically, we'll show you the Massa case study. You see here the Cordex evaluation scenario. We see also the Cordex RCP 4.5 scenario, and the time series for the Cordex RCP 8.5 scenario. Both this last from 2006 to 2099. This time series data sets have been passed to Julia, of course, like the others, to test, to try to do some statistical analysis to obtain the specific event scenario, and to analyze the return period of specific events. That's all for me. Try to be fast.
Okay, so you should be able to see my screen.
Yes.
Yeah, thank you very much. So hello everyone, I am Julia Anton, and I'm coming from Atlantic Technological University from Ireland. I am the project manager of the SCORE project, but beside the management of the project, I'm also involving in working on the technical task of SCORE, like this one. Today I will be talking about how we prepare the modeling scenarios through the statistical analysis for different living labs. First of all, let's see what's the extreme value analysis. This analysis seeks to assess the probability of events that are more extreme than any previously observed. So why this analysis is important? because extreme events, as you see in the slides that my colleagues presented, can have a significant impact of society, causing damage to property, infrastructure, and the environment. The extreme value analysis can be used to predict the likelihood of these events and to develop measures to mitigate their impact. So let's see how this analysis works. We mainly have 3 big steps. The first one will be the data processing, which means to gather the data on the variable of interest, such as rainfall, temperature, of wave heights, and we will look if we can identify any patterns to understand the variation. Then we need to identify and extract the extreme events from the time series data. Usually this is done by using different approaches, as you will see in my next slides. And the last step will be the model fittings, which aims to model the extreme events using the extreme value distribution. So this analysis has a range of applications, but I will mention the most important ones that we are considering for our project. So we have the flood forecasting, as it was the case with mostly our living labs. This analysis can practically be used to predict the likelihood and the severity of the floods. And another application can be the financial risk management, which we can use this analysis to assess the risk of financial losses due to extreme events. So there are multiple methods for calculating the extreme values, but the most used ones are the block maxima, the peak over threshold, and the point process approach. The block maxima is a method that focuses only on the maximum observation during each non-overlapping equal-sized interval of the observation period. This means that the data sets must be huge enough to perform this analysis. The peak over threshold is a method that works by specifying a certain high threshold and considering all observation above the threshold point in the analysis. So the choice of the threshold is an important step in extreme value analysis, and there are several methods for choosing a threshold, including the graphical methods, the Thompson's approach, the extreme value analysis R package, and as well the Solari approach. For this project, for calculating the return levels for different coastal city living labs, we tried all of these methods mentioned earlier, as you will see as well in the next slides. So the request was to calculate the return levels for different parameters like significant wave heights, the sea surface height, and discharge level. We found that block maxima method was the most appropriate for calculating the river discharge, while for sea surface heights and wave heights was the peak over threshold. On these slides on the left-hand side, you can see some results from Massa from Italy for calculating the threshold with different methods and how the return level will change based on that. So for this particular example, using the Thompson approach, we have a very low threshold, and so we have high differences in the return levels, while using the Anderson-Darling test, the threshold looks to perform that better and is quite close to the result that we have from the graphical method. On the table from the right-hand side, you can see an example of how we added all the results from the peak over threshold methods and the block maxima together so we put them together to choose the best approach to calculate the return levels for different RCP scenarios, as my colleagues already mentioned there. So all this analysis that was presented by me is freely available on Zenodo. So on Zenodo, we have a score community, and you can find the R script that I use to calculate the return levels for different CCLLs in our project. You have on this slide the DOI available so you can find it faster. So that's all for me. I hope you enjoy my presentation, and I'll give now the floor to the next speaker. Thank you.
Yes. So this is really the last mile. We also arrived to the goal. So the urban scale models, these are made by specific models. We say is the domain of hydraulics. So to specify what are these different elements we simulate riverbed, we simulate what happens in riverbed, simulate what happens in land, we simulate what happens in coastal area using possible coupled simulation. So essentially bidimensional 2D simulation on land and one-dimensional simulation in riverbed, as we may specify each river by simply its length and typical feature that is the river section. So this model are freely available, and these are a technical tool that is very well known in the world of hydrologists, hydraulic engineers, and so on. Is one of the open license modeling tools called CRAS. It can be easily installed in all the major operational system like Windows and Unix, and for instance, taking the case of the Massa study case, we can simulate the behavior of the Frigido River, and with respect to the extreme conditions that can be determined, as Julia said before. So we need a digital elevation model, as I said, and all the geometrical characteristic of the river. So we need to, I think, to create a geometry. So to insert all the geometry of the river, to create a terrain. So a layer, a digital elevation model that can be directly read by the model itself. And then within this computational framework, in which we have the one-dimensional river, or it can be two-dimensional river in some case of some simulation, and bidimensional floodable areas, in which, as you say, the specificity of each district are described. We are able to perform a simulation that still needs to be forced by initial condition and boundary conditions that are those of the models providing data at a specific point, at this section of the river basin, the section of the coastal areas, and finally, for instance, we perform unsteady simulation, taking, for instance, a triangular shape with the peak value associated to a specific return period. This is the hydrogram we wish to simulate. So water level, each water flooding maps is associated to a given return period. So a part of this very technical stuff concerning how to set up a simulation from the river side, but also from the coastal side, as also we read information from the wave models to simulate effects, flooding effects called wave run-up. So not only the so-called wave setup that is an average effect due to the sea level dynamics, but also the run-ups that is an instantaneous condition by the impact caused by the impact of sea waves along the coast. We are able to arrive to the goal, that is describing this kind of flooding maps. So, for instance, this is the flooding maps of Massa associated to the return period of 200 years and caused and computed using the time series provided by the so-called historical period. So, what is going to happen today with this kind of return time? While using, for instance, data from the last part of the RCP 45 scenario simulation, we have quite a different expected final simulation in which the flooded area is much wider than before. So you can see that taking the difference between the last scenario and the historical one. The same is happened also for Villanova for instance, which we compare the historical run with the return period of 200 years with respect to the what the expected conditions in the last part of this century. So with a remarkable difference, it is caused by, we guess, from the more intense storm and the internal effect of the expected climate change. We are at the end. In that, I'm sorry because we need more time than expected, but in describing methods and models for understanding the effects of climate change at the scale of our everyday life, I think we made two journeys. One is across scales. Now, so we say from the global scale, where we measure the effects of the ensemble dynamics of atmosphere and ocean, to the local scale, where we observe the effects closest to us. But actually, it was also a journey through time, as we simulate based on our current knowledge what has happened, what we say historical conditions, what has happened in the recent past, and what is supposed to happen by the end of this century and even beyond. I think it's very important to say that models are today an exceptional knowledge tool. They still are affected by uncertainty. So, but even an uncertain and error-filled environment remain the only way we have at our disposal to predict the long-term effects of climate change. So finally, as a take-home message, as we have the opportunity using models that are available to the entire scientific community and even beyond. These are all the models we present are actually community model that we may characterize by being open license or open source. Using this model freely available, we are able to make plans. Plans that affect our lives, not only our lives, but those of future generations, to design sustainable and socially acceptable adaptation solutions and to raise awareness among all citizens. I think a strong collaboration work has also to be performed with the other project partners in SCORE. For instance, in designing ecosystem-based solution for adaptation. And I think from this technical part of the webinar is all. Thank you for attention and sorry for being so late.
Thank you very much. So this was our last presentation. Thank you to all the speakers.